Testing a claim by the standard deviation, we are going to conduct a formal hypothesis test of a claim made about population standard deviation sigma or variance sigma squared, in which case the chi-square distribution is used in the case of a single variance or standard deviation. In this case, the test statistic chi-squared is n minus 1 s squared over sigma squared. The notation is very straightforward. N is again sample size, degrees of freedom is n minus 1, s is the sample standard deviation, sigma is the population one, s squared sample variance, sigma squared is the population variance. In this case, the p-value method, the critical value method, and the confidence interval method are all equivalent. However, it's important to see that due to limitation of a table, using those may not be easy, but you can do it by technology. The requirement, the sample is simple random sample. The population has a normal distribution, chi-square distribution. It is not symmetric. It is skewed to the right. It starts from 0 and it goes indefinitely on the right side. There is somewhere that you can find it on the internet. I've put the URL, the link. You can check it out if it works. Sometimes I've seen it that it doesn't work as properly. And let me know that can help you find the chi-square values, or simply use the table. To use the table, you need the area to the right, degrees of freedom, which is n minus 1. All right. So all values of chi-squares are non-negative, and the distribution is not symmetric. There is a different chi-square distribution for each number of degrees of freedom. The critical values are found in chi-square table using degrees of freedom n minus 1. So in chi-square table, each critical value of chi-squared in the body of the table corresponds to an area given in the top row of the table, and each area in that top row is a cumulative area to the right. Can't emphasize this enough. You remember that table, okay?
Assumptions for the chi-square test for variance or standard deviation. 1. The sample must be randomly selected from the population. 2. The population must be normally distributed for the variable under study. And 3. The observations must be independent of one another.
Let's just refresh everyone's memory as far as the chi-square is concerned. All right, so find the critical chi-square value for 15 degrees of freedom. So df is given, class. We don't need to subtract one, and that's important for you to pay attention to. df is 15 and alpha is 0.05, and we are dealing with the right tail test. So that means this. So look at the drawing. So the area to the right is 0.05. All you have to do, go to the table. Degrees of freedom is 15 and area to the right is 0.05. Very straightforward. Here's the table. You have 15, you have the area of 0.05, because remember the area to the right is what we need to do the math, and chi-squared becomes 24.996. Again, there is a place that you can program chi-square, chi-inverse into a TI calculator. I am giving you the program, I'm giving you the YouTube, you can look it up. I've seen that most of the time this works, sometimes it doesn't, but try this class, okay? If you're interested in using technology, that's fine. And so it is a long process. Honestly, for a simple case like that, it is much easier to look up the table. Okay, so this is how you look it up. In the second case, the degrees of freedom is again given. It's 10, alpha is 0.05, but this time it's left tail. Therefore, the area to the right is 0.95. And therefore, if you want to do the reading, okay, the area to the right is 0.95. If you want to do the reading, take a look. You have to look at the area, which is 0.95. I can't emphasize this enough. This is because of the way the table works. So the answer is 3.940. 3.940. Here's the next one. We're going to find the critical chi-square value of 22 degrees. Again, degrees of freedom is given. You don't have to subtract one. So that's fine. That means you're looking at this one. It's a two-tailed test. Alpha is 0.05. So you draw the graph. 0.95 is smack in between. 0.05 divided by 2, which means 0.025 on each side. Now, what do we need? We need degrees of freedom, which is 22. Fine. How do we arrive at the answer for chi-squared of the left and chi-squared of the right? We need the area to the right. Now, chi-squared of the right, the area to the right is 0.025. It's a very obvious class. But what about the chi-squared of the left? Is 1 minus that. Everything is almost to the right of that. So 1 minus 0.025. So degrees of freedom is 22. That's what you're looking at. Area is 0.025 for chi-squared of the right and 0.975 for chi-squared of the left. Again, I want to make sure you see how we arrive at it, okay? So you need the area to the right. So for the case of chi-squared of the left, the area to the right is 0.95 plus 0.025, which is 0.975. In other words, add this number and add this number, or simply put subtract this number from what? Okay, 1 minus 0.025, that would be the fastest. 1 minus 0.025, which gives you 0.975. Okay, so you go to the top, you look at 0.975, that's one of it. Okay, and you look at 0.025, that's another one. The numbers in front of 22, those are the numbers you're looking for. This is the chi-squared of the right, this is the chi-squared of the left, and those are the numbers.
An instructor wishes to see whether the variation in scores of the 23 students in her class is less than the variance of the population. The variance of the class is 198. Is there enough evidence to support the claim that the variation of the students is less than the population variance? Sigma squared equals 225 at alpha equals 0.05. Assume that the scores are normally distributed.
So let's see what's given. The score of 23 students, and in her class is less than the variance of the population. The variance of the class is 198. So 198, the variance of the class, the variance of 23 subjects. And so that's S squared. Sigma squared is 225, alpha is 0.05, and we are going to do the test statistic. So what do? H0, sigma squared equals 225. But what is H1? So what are we checking? Is there enough evidence to support the claim that the variation of the student is less than, and that is the claim. The next one is using the top formula to find the test statistic. Everything is given, n is given, s squared is given, sigma squared is given. By the way, most of the time, s and sigma are given, so you square. So you calculate that by simply putting in, and it gives you the number. A couple of decimals will do the job. So the next step is to find the critical value, okay, which comes from the choice of alpha. Alpha is 0.05, degrees of freedom is n minus 1, which is 22, okay, and we use the table, okay, and we've seen that. You should have no problem with that. In fact, even the previous page has the number under 22, remember that? So we get this, and now it's a matter of comparison. So when you compare step 2 and 3, when you compare the location of test statistic and the critical value, it's to the right of it, and this is a left tail test, so that it's way into the non-rejection region. So the process repeats itself just the way we have learned it before. It works out exactly in the same manner. So if we know the test of hypothesis, you see the steps, The thing that is going to change is really step 2, calculation of test statistic. The process is identical for the rest of it. Step 1, you write H0 and H1. Step 3, critical value from the choice of alpha. Step 4, decision making. What about step 2? You need a formula sheet. And you need to know what formula you're using. Are you using the Z, the T, the chi-squared formula, which one? Okay, and that's why it's important to read and understand and distinguish. And so, according to this, if it's in way to the non-rejection region, fail to reject or do not reject H0. So if you're not rejecting H0, in essence, you're rejecting H1. Rejection of H1 means the claim must be false. So I hope you see again how we get to the decision. Don't reject H0. I want to make sure everybody understands this is the one that comes from our calculation. Calculation gives us only this one. The rest, now we go back to step 1, look for the location of a claim and answer it. So part B, you go back to step 1 and you find the location of a claim, you answer it. Part C, always there is or there is not sufficient evidence to support the claim. And then you do the writing for the claim. Part A is from the calculation, comparison of 2 and 3. Part B comes from step 1, locate claim, figure out which one is which and what's your answer. Part C, you just write accordingly. Alright, so having said that, here's using TI. You can go to second variables, chi-squared CDF, and you put 3 entries, the left bound, right bound, and so forth. So the lower bound, and that can give you the chi-squared 0.37994. What does it mean? This is your p-value. If you go this route, you're calculating the p-value, chi-squared CDF, and what do you put as your upper value is your test statistic. Why upper? Because the left tail test, I want you to understand, it's not always upper. If it's a right tail test, that would be your lower, and upper becomes like a large number, 1,000 or 10,000. So it's important to see how we are arriving at this. According to the p-value, this is way larger than alpha, and therefore we get to the same result. So this will give you the same result of part A of the decision, and then you continue by it.
A researcher wishes to test the claim that the variance of the nicotine content of a cigarette manufacturer is 0.644. Nicotine content is measured in milligrams and assumed that it is normally distributed. A sample of 20 cigarettes has a standard deviation of 1 milligram. At alpha is equal to 0.05, test the claim that the variance of the nicotine content of its cigarettes is 0.644.
So let's see what's given. We are dealing with a normal distribution, and we are testing the claim that the variance is 0.644. So this is sigma squared, and we are checking that to be equal to that, okay? So that is the claim, that is sigma squared equal to that, okay? That is H0, and because we are checking that, it becomes a two-tailed test, and it's not equal, becomes H1. In any event, so what do we do to check that? We come up with 20 samples. That's N. And the standard deviation for the N is 1. So that's S. Alpha is 0.05. And so sigma squared, N is 20, sigma squared is 0.644, S is 1, alpha is 0.05. So I explained how we test the claim. Test the claim that the variance of the nicotine content of a cigarette is equal to, that means H0 sigma squared is equal to 0.644. That's the claim. And H1 sigma squared is not equal to 0.644. And what happens, it makes it a two-tailed test. Test statistic uses the top formula. We calculate the chi-squared equals n minus 1 s squared over sigma squared. Everything is given up. What I want you to pay attention to S is 1 and 1 squared happen to be 1 also. But just so we don't make a mistake, when I put it down, I don't put 1, I put 1 squared. Because if it's anything other than 1, then when you square it, it gives you a different answer. So make sure you square that, because S squared is not given, it is only S that is given. And so you plug in, you calculate, and you end up with the form. And so what happens next, you need the critical value. Alpha is given as 0.05. Degrees of freedom is n minus 1, 20 minus 1 or 19. What about the critical value? There are two of them. There are two critical values. Why is that? Because it's a two-tailed test. Alpha is 0.05. Degrees of freedom is 19. You look up the table. You end up with those numbers 8.907 as chi-squared of the left. This is called chi-squared of the left. And this is 32.852 is chi-squared of the right. And so the test statistic is in between non-rejection region. So with that being the case, you don't reject H0. If you don't reject H0, so that is the decision that you are going to make when it comes to this question as your part A. That's all it does. Your calculation gives you part A. Do not reject or fail to reject H0. Now you go back to step 1 and look at the location of a claim. Claim is sitting to H0. If you're not rejecting H0, you're not rejecting the claim. The claim is therefore true, so there is sufficient evidence to support the claim. And you do the writing. There is sufficient evidence to support the claim that the variance of the nicotine content of its cigarettes is 0.644. Why do we test a claim about the standard deviation or variance? The common goal in business and industry is to improve the quality of goods or services by reducing variation. Quality control engineers want to ensure that a product has an acceptable mean, but they also want to produce items of consistent quality so that there will be few defects.
If weights of coins have a specified mean but too much variation, some will have weights that are too low or too high, so that vending machines will not work correctly, unlike the stellar performance that they now provide.
This is an example that why we want to test that, and we are interested in having proper standard deviation. Here's the next example.
A simple random sample of 37 weights of post-1983 pennies has a mean of 2.49910 grams and a standard deviation of 0.01648 grams. U.S. Mint specifications require that pennies be manufactured so that the mean weight is 2.5 grams. Use a 0.05 significance level to test the claim that the population of weights has a standard deviation less than the specification of 0.0230 grams.
The first thing is to read and reread and reread until we understand what's given. So the very first number, 37. What is that? Can anybody tell us what's 37?
10.
Beautiful. Then the next number is 2.49910 grams. What is that? It pertains to those 37.
It's the H.
I'm sorry, one more time. What was it?
The H value.
H? What is the H value? No.
The X bar?
X bar. It's the mean. When it's the mean, it's either X bar or mu. What is the next one?
S.
Very good. That's the standard deviation, but it pertains to those subjects, 37. What is 2.5?
Mu.
Mu, because it's supposed to be that for all, for the population. This is mu. Significance level, obviously, alpha. Finally, I see this number. What is that? We are testing the claim that the population of weights has a standard deviation less than this, so this must be sigma. It's a simple random sample, short SRS, N is 37, X bar is 2.4991 grams, S is 0.01648 grams. Why is that? Because it pertains to those 37 samples. H0 and H1, we want to check that the standard deviation is less than that. That's the left tail test. So sigma is 0.023. and of course with the units grams. H1 says sigma is less than that, and it makes it a left-tail test. And that is also the claim. So in your very first step, you have a lot of information for your reader. So right away, we recognize because we are dealing with sigma, what do? Our test statistic must be chi-squared. Why is that? We are dealing with sigma and we are dealing with one population. We are comparing the sigma or sigma squared, in this case sigma, with a number. That means use chi-squared. So you use the top right formula, plug in, and it gives you the answer. 18.483. That is your test statistic. What is it equal to? 18.483. You are going to come up with the critical value. This is a left tail test. Alpha is 0.05. Degrees of freedom is n minus 1 over 36. And the total area to the right is 1 minus 0.05 or 0.95 for the sake of reading. Table doesn't give you an answer. So it's between those two numbers because the degrees of freedom is not there. I'll show you in a moment. And technology gives you obviously a number in between because it can. In a matter of comparison, as you can see, even though we don't have the answer, we know for sure the critical value is larger than 18.493. Even that one is larger than test statistic. That means it puts us in the rejection region. So take a look at this. Your test statistic is 18.483. Even if you go with the table, even if you use this one rather than this one, using 18.493, it is still less than that. So no matter what, you are going to reject H0. So because you are rejecting H0, what do? You go back to step one and take a look at the location your claim. If you are rejecting H0, loosely put, you are accepting H1, and therefore the claim becomes true. And so there is sufficient evidence to support the claim. You start writing the whole thing as you would. So we are looking at the area to the right, which is 0.95. So I'm looking at the area to be 0.95. Okay, area to the right. And the degrees of freedom is, look at this number 30. Okay, look at this number 40. So the degrees of freedom is missing. 36 is not there. So I don't have the answer, but look at this one. According to the table, the answer is between these two values, 18.493 and 26.509. This is how you look up a table, and this is why we say it's a limited table.
Listed below are the heights in centimeters for the simple random sample of female supermodels. Use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than sigma equals 7.5 centimeters for the population of women. Does it appear that heights of supermodels vary less than heights of women from the population? Assume normal distribution.
We are given the information in the form of a data rather than statistics, so we have to figure it out on our own. This is the sample. We are assuming normal distribution. Sigma is given as 7.5, and there are 16 pieces of data. So that's given. And you have to put it into a technology because 16 pieces, it takes a little bit of a time if you want to calculate what. If you look at the top right formula, everything is there. The only missing is S. You have to calculate that. I'm going to assume you put it into calculator, a technology, and you come up with S. Sigma, 7.5 centimeters. Does it appear that heights of supermodels vary less, which means sigma is less than 7.5 centimeters, and that is the claim. That's the left tail test. So, with that being the case, we use the top right formula to come up with the answer. We just plug in, and it gives us the answer, and we end up with 0.9 0.907 as the answer. So the test statistic results in 0.907. What about the critical value? Critical value comes from the choice of alpha. Alpha is 0.01. That means since it's a left tail test, we need the area to the right. 1 minus that for the sake of reading from the table. So the area to the right is 0.99. Degrees of freedom is n minus 1 is 15. And we get 5.229. With that being the case, where is this 0.907? This is way into the rejection region, is to the left of 5.229, as you can see from the graph. And therefore, you reject H0. The very first part of the decision, part A, is to reject H0. If you reject H0, now you go back to the very first step and figure out where the claim goes. The claim belongs to H1. You are rejecting H0. That means you loosely put accepting H1. Therefore, the claim is true. So therefore, there is sufficient evidence to support the claim. You do the right. So reject H0. The claim is true, therefore. All of this calculation is about the very first part. And then you go to the first step to figure out where the claim is and answer. So there is sufficient evidence to support the claim that female supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of them. Let's go to the next one. If we want to do this by the p-value, and again it's limited, in case the table doesn't have what you're looking for. Remember what the p-value is. If I go back to the previous page, the test statistic was calculated as 0.907. So the area to the left of 0.907 is your answer. Okay. By the way, you can check the normality. This is all using technology. Okay. So if we go with the technology, look at the p-value from technology. The p-value is less than 0.0001, which is clearly less than alpha of 0.01. And therefore, you get to the same decision for part A. Reject H0. And then you write the rest of them accordingly. So as far as the table is concerned, n is 16, which means the degrees of freedom is 15. And you want to see if you can figure out the area to the left of that, 0.907. So the limitation is there. Let me see if I can show you the table again. So degrees of freedom is 15. This is what you're looking for. N minus 1. Area to the right. Remember, alpha is 0.01. So if you look at the area of 0.99 and 0.995 at top, it gives you the area in between, and the p-value is less than 0.01. Okay, look at all these numbers. Okay, it doesn't have the number we want. So let me write the test statistic. What was the test statistic? Test statistic was chi-squared of 0.907. So as you look at the numbers get larger and larger to the right. So the number we want is not there, but clearly is to the left of the last number on the left, which is 4.601. And I want you to look at the area at top. The area at top is 0.995. What is that area? To the right of it. So what you want is the area to the left of it, which becomes the alpha. So what is the p-value less than, according to the table? P-value, according to the table, take a look at the number at top, is less than the top number minus 1. And this is 0.005. So we don't know the p-value, but we know for sure it's less than 0.005. So we get to the same result as we did when we did the critical value, the traditional method, and we rejected H0. Let's go to the last part of this question. So basically, for a case like this, it is expected that you be comfortable with technology. If we were to use the confidence interval, remember the test is a left-tail test with the alpha of 0.01. This is what we have discussed. So if alpha is 0.01, confidence level of 98%. If 0.01 is a one-tail test, it doesn't matter left or right, then it corresponds to 98% confidence level. If it's a two-tail test, then it's 99%. It's complementary. So with that being the case, you want a 98%. So with that being the case, we just use the formula n minus 1 s squared over chi squared of the right less than sigma squared, n minus 1 s squared over chi squared of the left. This is the formula we see in the previous chapter when we did with the confidence interval. So we have 98% in between because this was 1%. We put another 1% on the right, okay, to make it 98% in between. So you need to look up the chi squared of the left here, chi squared of the right for degrees of freedom of n minus 1 or 15, and you use them accordingly. With that being the case, remember we calculated the S in the very first page that we encountered this question. That's why S is 1.84399. So now plug in. That's all you have to do, plug in. Now chi squared of the left and right are looked up from the table. I highly recommend you do that on your own. You'll be able to do that. You should have no problem with that. Now this is the sigma square. And remember what happens to sigma. Sigma, you just take a root. It's between the two. All right. Take a root between 1.2915 and 3.1223. With this confidence interval, we can support the claim that sigma is less than 7.5. Why is that? Because all values of the confidence interval are less than 7.5. In other words, both numbers, the number on the left as well as the number on the right, and this is what we are comparing with, both of them are less than 7.5.